Hi everyone, thank you for watching this video. I'm a master student affiliated with UST and CLIC. What I want to share with you is my thesis contents. The title of my thesis is Fabrication and Evaluation of Biodegradable Alginate Bead Control Release Fertilizer or the Control Release on Nitrogen. Have you ever heard about CRF, which means Control Release Fertilizer? Recently, control release fertilizer, which functions based on similar principles to drug delivery systems, have been developed to reduce fertilization loss. Coated type of CRFs have a sustained release rate that is dependent on the coating thickness, thus providing a continuous supply of nitrogen-based nutrients to the soil. Control release fertilizer (CRF) are next generation type of fertilizers with several advantages over conventional fertilizer. For example, CRF can reduce the number of fertilization and nitrogen loss in soil than the previous type of fertilizer. However, current type of CRF paradoxically accelerates breaking the balance of environment because the outer membrane of CRF consists of non-degradable and petroleum-based plastics. For instance, Ligetto and Miller reported that high amounts of microplastics accumulate yearly in farmland in European and North America respectively, emphasizing the need to develop highly degradable and biocompatible CRFs for sustainable environment. Recently, alginate has gained considerable attention as a promising eco-friendly coating material. Alginate is a polysaccharide in brown algae and is widely used as an encapsulating agent, owing to its simple and unique process. The egg box structure formed by alginate can be utilized to produce biodegradable hydrogel bead in the presence of divalent cation, such as calcium cation. In the present study, alginate bead were prepared by Mn plus ions. The G-box in alginate molecules can form a chelated structure by coordinating metal ions into an egg box morphology. However, beads absorb water and swell rapidly owing to their hydrophilic nature, indicating the need for further modification. Therefore, the aim of this study was to develop a highly degradable, non-toxic, and biocompatible CRF based on calcium arginate beads. To achieve this, a modified calcium arginate CRF system was fabricated by introducing polyvinyl alcohol, citric acid as additional cross-linking chemicals, and humic acid as a physical barrier and chelating agent to increasing nitrogen use efficiency. PVA and CA were chosen as additional material for the calcium arginate bead to introduce chemical cross-linking to enhance the physical properties of CRF coating and decrease fertilizer release rate. Humic acid, HA, an organic compound that can improve soil health, was incorporated into system to function as a mesh-like material in the synthesized CRF and as chelating agent, owing to its various chemical groups. The effect of CRF on carrot growth was examined, and the release rate and profile of CRF were evaluated by analyzing soil leachate. Additionally, the urea release behavior of calcium arginate CRF in water medium was evaluated. Calcium arginate bead can be fabricated by transferring sodium arginate droplet into calcium chloride solution forming an immersion reaction. The spherical pocket can hold substance, and its capacity can vary with the concentration of sodium arsenate and calcium chloride. Therefore, the characteristics of basic calcium arsenate bead, including sphericity and diameter, were determined prior to incorporating urea. The result of the present study shows that the sphericity of beads increased with increasing concentration of sodium arsenate and decreasing concentration of calcium chloride. Generally, a perfect sphere has a sphericity of 1. Since calcium chloride provides calcium cation to the chelating system, it functions as the cross-linking point that determines the overall morphology of the bead. Therefore, an increasing in calcium chloride concentration can cause an inverse increase in cross-linking density, resulting in steep structured bead. In contrast, an increase in the concentration of relatively flexible GG unit can promote the fabrication of highly spherical bead. Highly spherical beads tend to have lower surface area compared with non-spherical beads, which can reduce contact with water, thus delaying the release rate of captured material. Interestingly, the finding of present study shows that the sphericity of bead increased with increasing sodium arsenate concentration at high calcium chloride concentration, which was attributed to high chelating capacity of sodium arsenate owing to its high viscosity. Further analysis of the effect of gelation time and the concentrations of sodium arsenate and calcium chloride shows that the sphericity of the bead increased with decreasing calcium chloride and increasing gelation time. In contrast, the sphericity of bead prepared using high concentration of sodium arsenate and calcium chloride remained unchanged with increasing time, indicating that the viscosity of bead increases rapidly, reaching the maximum at high concentration of both the chelating and the cross-linking units. Figure S1 indicates the optical images of different CRF beads. Contrast is added to make it easier to observe with the naked eye. In result, as the gelation time and calcium chloride concentration increased, it was confirmed that opaque beads were formed. It appears to be a phenomenon caused by an increase in the degree of cross-linking. The effect of urea addition on the viscosity of sodium arsenate suspension was examined, as shown in Figure 3. Viscosity is an important determinant of the quantity of the bead when extrusion dripping method is used for fabrication of calcium arsenate bead. The result of the present study shows that there was a significant decrease in the viscosity of sodium arsenate suspension with increasing the concentration of urea. Adding urea in water medium causes increasing the pH of the environment, which induces the ionization of COH functional groups of sodium arsenate to form COO-. The negatively charged functional groups creates an electrostatic repulsion between ions, which increases the mobility of sodium arsenate and lowers its viscosity. The effect of calcium chloride concentration of UL efficiency of CRF bead were examined. There was a steady decrease in UL efficiency of the bead with increasing concentration of calcium chloride, as shown in Figure 4. An increase in concentration of cross-linking points could lead to highly dense structure of the bead, which can expel urea from the core. However, there was a significant decrease in urea release rate with increasing concentration of calcium chloride, corresponding to UL of 80 and 60% respectively. These results indicate that the UL and release rate of the bead exhibit an inverse relationship. The UL efficiency of the bead was not significantly affected by increasing gelation time at calcium chloride concentration of 10%, as shown in Figure 4b. The non-significant difference in UL of the bead with increasing gelation time could be related to the mobile capacity of the bead structure. The short gelation time of 30 minutes is insufficient for the formation of the egg box structure, resulting in multiple defect points, which can negatively affect the structure and stability of the bead during the dry reswell process. Moreover, the similar UL efficiency of the bead at 30 and 60-minute gelation time indicates that the structure of the bead was highly stable. Additionally, the dry reswell process can increase the stability of beads fabricating using 10% of calcium chloride and gelation time of 60 minutes by reducing excessive free space in the core bead. Additionally, the diameter of the dried bead according to the concentration of calcium chloride, additional gelation time, and composition of calcium arginate bead are examined. Especially the diameter of the bead decreased with increasing gelation time from 0.5 to 2 hours. In the present study, 3 eco-friendly materials were used to modify the fabricated calcium arginate CRFs to inhibit the rapid release of urea. Condensation reaction occurred during the fabrication process, which produced ester between COOH groups and the OH groups of PVA, HA, and CA, and 3 multifunctional molecules form crosslinks. The addition of PVA, HA, and CA enhanced the metrics of the bead, but decreased their UL, which is urea loading efficiency, which could be attributed to competition between urea and the additives or limited free space in sodium arginate chains. Fertilizer is usually used in crop production to improve soil nutrient level to support optimal plant growth and yield. However, in this present study, we examine the growth inhibitory effect of excess nitrogen on carrots. Carrots require only a small amount of soil nitrogen for optimal growth. In this study, the topsoil was mixed with vermicompost, thus providing some amount of soil nitrogen. Additionally, nitrogen was supplied in the form of urea or calcium arginate CRFs to induce excessively high soil nitrogen levels. The soil were analyzed to measure controlled release effect. The controlled release effect of CRF was determined by analyzing the nitrogen contents of the soil after harvest. Compared with soil-supplied CRF, control soils and soil-supplied urea had significantly lower finer nitrogen contents, which could be attributed to the leaching of organic nitrogen in the soil by watering during the cultivation period. In contrast, soil-supplied CRF had higher finer nitrogen content compared with initial content prior to cultivation and CRF addition. Regarding soil-supplied CRF containing 5% arginate without additives, which is called 5C, the residual nitrogen level was similar to that of soil in the control group, indicating the rapid release and exhaustion of urea prior to cultivation. However, soil-supplied CRF containing 10% arginate without additives, which is called 10C, had relatively higher amounts of residual nitrogen. It indicates that the bead had a better control release effect of urea. Interesting, the additives significantly suppressed the rapid release of urea from CRF. Furthermore, the addition of humic acid increased the residual nitrogen contents of the soil, which was consistent with the nitrogen content of leachate collected weekly, as shown in Figure 8 and Figure S3. Generally, humic acid prevents the leaching of organic nitrogen by acting as natural chelate. Regarding soil-supplied urea, there was considerable loss of nitrogen during the cultivation period via leaching. However, soil-supplied CRF containing 10% of arginate lost only approximately half the amount of nitrogen lost by soil-supplied urea. Furthermore, the addition of humic acid increased the residual nitrogen contents of soil, which was consistent with the nitrogen contents of leachate collected weekly, as shown in Figure S3. Generally, HA prevents the leaching of organic nitrogen by acting a natural chelate, degrading soil-supplied urea. There was considerable loss of nitrogen during the cultivation period via leaching. However, soil supplied with CRF containing 10% of urea lost only approximately half amount of nitrogen lost by soils supplied urea. So as I have seen in this presentation today, calcium arginate bead containing urea were successfully fabricated and optimized via extrusion dripping method. The bead were formed through cross-linking reaction between the arginate chains by calcium cations, and the higher degree of cross-linking, the lower the release rate of urea. The addition of humic acid, PVA and CA reduced the release rate by strengthening the structure of the bead. The addition of humic acid can improve the nitrogen use efficiency after degradation of CRF bead. Additionally, carrot grown in soil supplied CRF were smaller in size owing to excess supply of nitrogen. It indicates that CRF sustained continuous nitrogen use and nitrogen release in the soil for the 90 days of cultivation period. Overall, the fabricated CRF maintained continuous release of nitrogen. However, the additives improved the stability of CRF, which could support plant growth during after the decomposition of the bead. The fabrication process applied in this study is easy and could be applied for the mass production of CRF containing urea. The co-solvent used for both sodium arginate and calcium chloride was water, which has several advantages. One of it is that the use of water could facilitate the mass production of the bead. Additionally, since the fabrication procedure involves a dry swell process, which involves the gradual drying of water in the bead containing urea, the release rate of fertilizer will be limited. Finally, the process adopted in this study is flexibility, and it is possible to add functional materials to further improve the release rate, stability, and mechanical strength of the bead. Functional material should be either water-soluble or dispersible in water to facilitate rapid fabrication. References were made to the following literature: